Look up at the night sky on a clear dark night, far from city lights. If you are lucky, you will see a faint band of light stretching from horizon to horizon, pale, diffuse, like someone smeared a thin wash of white paint across the darkness. That is the Milky Way. Not the whole thing, just a cross-section, a slice through the middle of the structure you are standing inside. And here is the thing that should stop you cold the moment you really think about it. Every photograph you have ever seen of the Milky Way from the outside, the sweeping spiral arms, the bright central bulge, the elegant disk shape floating in space, none of those images are real, not a single one of them. Because no human being, no spacecraft, no telescope we have ever built has ever been outside the Milky Way to take that photograph. We are inside it. We have always been inside it. We are 26,000 light-years from the center, embedded in one of its spiral arms, surrounded on all sides by hundreds of billions of stars, with dust and gas blocking our view in most directions. And yet we have produced detailed maps of its structure. We have measured its spiral arms. We have calculated its mass, its rotation, its age, its diameter. We have identified the supermassive black hole at its center. We have done all of this without ever leaving. And the way we did it is one of the most remarkable stories in the history of science. Let us start with the problem in its full severity, because it is worse than it sounds. Imagine you are trying to map a forest, but you are standing in the middle of it. Trees surround you in every direction. You cannot climb above the canopy to get a bird's-eye view. You cannot walk to the edge because the forest is so large that walking to the edge would take longer than your entire lifetime. All you have is what you can see from where you are standing, and in most directions, your view is blocked after a few hundred meters by the trunks and the leaves of the trees immediately around you. How do you map something you can never see from the outside? That is the problem astronomers faced when they first started trying to understand the structure of the Milky Way, and for a very long time they could not solve it. But before we get to how they eventually did, it is worth pausing on what that faint band of light in the night sky is actually showing you. When you look at the Milky Way from a dark site, you are looking along the plane of the galactic disk. The disk is roughly 100,000 light-years across, but only about 1,000 light-years thick at our location. When you look in the direction of the disk, your line of sight passes through a much greater depth of stars than when you look perpendicular to it. The band appears bright because you are looking through a far larger column of stars in that direction. When you look up or down, out of the plane, your line of sight exits the disk quickly and enters mostly empty space. Fewer stars, less light, darker sky. It is like looking at the edge of a dinner plate from the surface of the plate itself. You can tell it is flat and disc-shaped from the edge view, but you cannot see the full shape because you are sitting on it. This observation, that the band of the Milky Way is a disk seen from inside, was understood correctly by astronomer Thomas Wright in 1750. The disk shape was deduced from the night sky alone, centuries before anyone had the tools to measure it in detail. The first serious attempts to map the galaxy, in the early 20th century, used star counts. Astronomers would look in a particular direction, count how many stars they could see, and use that count to estimate how far the galaxy extended in that direction. This method produced a map that placed our solar system near the center of a relatively small galaxy. It was completely wrong, not slightly wrong, fundamentally, structurally, directionally wrong. And the reason it was wrong reveals something crucial about how difficult this problem actually is. The problem is dust. The Milky Way is not just stars, it is full of interstellar dust. Tiny particles of carbon and silicates scattered throughout the disk of the galaxy. This dust is almost completely transparent to our eyes. You cannot see it directly, but it absorbs and scatters visible light. When you look toward the center of the galaxy in visible light, the dust between us and the center absorbs most of that light before it reaches us. The early astronomers who counted stars were not seeing the whole galaxy. They were seeing a bubble of stars around us within which visible light could travel before being blocked by dust. The galaxy extended far beyond that bubble in every direction, invisible to any optical telescope. The early maps showed our solar system at the center, not because we are at the center, but because the dust made everything equidistant in every direction from our point of view. It was one of the most significant observational errors in the history of astronomy. The breakthrough came in 1951, and it came not from visible light, but from radio waves. Radio waves pass straight through interstellar dust. As if the dust is not there, they are not absorbed or scattered by the tiny particles that block visible light. And hydrogen, the most abundant element in the universe, emits a very specific radio frequency, 21 centimeters, when its electrons flip between energy states. This 21 centimeter emission is detectable across vast distances, straight through the dust that makes optical observation useless. In 1951, astronomers Harold Ewan and Edward Purcell at Harvard detected this hydrogen signal for the first time, and within a few years, radio astronomers around the world were using it to map the distribution of hydrogen gas throughout the galaxy, tracing the structure of the spiral arms by following where the hydrogen was concentrated. But mapping the structure of the galaxy is only half the problem. The other half is distance. Knowing that a radio signal is coming from a particular direction tells you where something is in the sky. It does not tell you how far away it is. And without distance, you cannot build a three-dimensional map. You can only plot directions. To turn a direction into a position in the galaxy, you need to know how far away the source is. And measuring astronomical distances is one of the hardest problems in all of science. The solution to the distance problem came in layers, each one building on the previous. The first layer involves nearby stars. For stars within a few thousand light-years of Earth, astronomers can use a technique called parallax. Hold your finger in front of your face and look at it with one eye, then the other. Your finger appears to shift position against the background. The closer your finger is, the larger the apparent shift. The same thing happens with nearby stars when you observe them from opposite sides of Earth's orbit around the Sun. In January, Earth is on one side of the Sun. In July, it is on the other side, 300 million kilometers away. Nearby stars appear to shift slightly against the background of more distant stars. The size of that shift directly gives you the distance. This works well for stars within a few thousand light-years. Beyond that, the shifts become too small to measure reliably. The second layer involves a special type of star called a Cepheid variable. Cepheid variables are stars that pulsate. They swell and shrink in a regular cycle, brightening and dimming as they do. In 1912, astronomer Henrietta Swan-Leavitt discovered something extraordinary while studying Cepheids in the Small Magellanic Cloud. She found that the period of a Cepheid's pulsation, how long it takes to go from bright to dim and back, is directly related to its true luminosity. The longer the period, the more intrinsically luminous the star. This is called the period-luminosity relationship, and it is one of the most powerful tools in astronomy. If you know a star's true luminosity and you measure how bright it appears from Earth, you can calculate exactly how far away it is. Cepheids became the first standard candle, a reliable ruler for measuring distances across hundreds of millions of light-years. It was Cepheid variables that allowed Edwin Hubble to prove in 1923 that the Andromeda Galaxy was not a nebula inside the Milky Way, but a separate galaxy more than 2 million light-years away. And it is Cepheids, extended and refined over a century, that gave us the ability to place objects at known distances throughout the galaxy and beyond. But here is where it gets genuinely strange. Because even with radio waves penetrating the dust and Cepheids providing distance measurements and decades of painstaking survey work, our map of the Milky Way is still incomplete. And the most recent revisions to that map have overturned assumptions that astronomers held for decades. For most of the 20th century, astronomers believed the Milky Way was a relatively simple two-armed spiral. two major arms winding outward from the central bar, clean, symmetrical, elegant. Then, in the 1990s and 2000s, increasingly precise radio surveys began revealing that the structure was messier, more arms, more branches, more complex intersections. By 2008, a comprehensive survey using the Very Long Baseline Array, a network of radio telescopes stretching across North America, had mapped the positions of star-forming regions throughout the galaxy with unprecedented precision. The result was a four-armed spiral, more complex than anyone had realized, with our solar system sitting in a minor arm called the Orion Arm, or sometimes the Orion Spur, between two of the major arms. And then Gaia changed everything. In 2013, the European Space Agency launched a spacecraft called Gaia. Its mission was to measure the positions and distances of stars with a precision never before achieved. Not thousands of stars, not millions, over 1 billion stars, each one measured to an accuracy that makes previous surveys look rough by comparison. Gaia uses parallax, but with instruments so sensitive that it can measure parallax shifts for stars tens of thousands of light-years away, far beyond the range of any previous technique. By 2022, Gaia had released its third major data catalog, containing detailed measurements of nearly 2 billion stars. Astronomers are still working through that data. What has emerged from the early analysis is a picture of the Milky Way that is significantly different from what was believed just a decade ago. The galaxy is warped. The disk of the Milky Way is not flat. It curves upward on one side and downward on the other, like a vinyl record left in the sun. This warp was known in rough outline before Gaia, but Gaia revealed its full extent and complexity. It is not a gentle curve. In some regions, the warp raises the disk by several thousand light-years above the plane. The cause of this warping is still debated. The most likely explanation is a past gravitational interaction with a satellite galaxy, possibly the Large Magellanic Cloud, which is currently on a close approach to the Milky Way and whose gravity is distorting the outer disk. But the details are still being worked out. Gaia also revealed that the Milky Way has been involved in multiple mergers with smaller galaxies over its history. Stars from these consumed galaxies are still present in the Milky Way today, identifiable by their distinct chemical compositions and orbital patterns. In 2018, astronomers analyzing Gaia data identified the remnants of a large ancient galaxy that collided with the Milky Way roughly 10 billion years ago. They called it Gaia-Enceladus. It contributed billions of stars to what is now the inner halo of the Milky Way. The galaxy we live in is, in part, the debris of galaxies that no longer exist. But the most disorienting discovery from Gaia is about the spiral arms themselves. They are not permanent structures. They are waves. Density waves moving through the disk of the galaxy like ripples on the surface of a pond, compressing the gas and dust as they pass and triggering bursts of star formation. The stars that fill the spiral arms are not the same stars that were there 1 billion years ago. Stars move through the arms and out the other side. The arms persist, but the matter inside them is constantly changing. The structure we call the Milky Way's spiral arms is not a fixed architectural feature of the galaxy. It is a pattern, a recurring compression wave that has been moving through the disk for billions of years. The image we have of our galaxy as a stable, well-defined shape is in a sense an illusion, a snapshot of a pattern that is always in motion. And there is the question of what we still do not know. The center of the Milky Way is hidden behind so much dust that even radio waves struggle to penetrate it completely. The far side of the galaxy, the side directly opposite us from the galactic center, is the least mapped region of our own home. We know less about the structure of the Milky Way on the far side of its center than we know about the surfaces of planets in other solar systems. In 2019, the Chinese radio telescope FAST began a survey specifically designed to map the far side of the galaxy using the 21-centimeter hydrogen signal. That survey is still ongoing, The results are still coming in. The map is still being drawn. There is one more piece of the puzzle that reveals how strange and incomplete our picture of the galaxy truly is. It involves how the Milky Way rotates. In the solar system, the planets closer to the Sun orbit faster than the planets further away. Mercury completes an orbit in 88 days. Neptune takes 165 years. This makes intuitive sense. The closer you are to the gravitational source, the faster you move. You would expect the same pattern to apply to stars in the galaxy. Stars closer to the galactic center should orbit faster than stars further out in the disk. In the 1970s, astronomer Vera Rubin and her colleagues measured the rotation curve of galaxies, mapping how orbital speed changes with distance from the center. What they found was profoundly wrong. Stars in the outer disk of the galaxy were not slowing down with distance. They were moving at roughly the same speed regardless of how far from the center they were. The rotation curve was flat, where physics said it should fall off. The only explanation that worked was that there was far more mass in the galaxy than the visible stars and gas could account for. A vast, invisible halo of matter surrounding the entire disk, providing the gravitational pull needed to keep the outer stars moving at the speeds they were measured to have. This is dark matter. We cannot see it. We cannot detect it directly with any instrument. We know it is there only because of what it does to the rotation of the galaxy, and it outweighs everything we can see by a factor of roughly 5 to 1. The Milky Way we can observe, all the stars and gas and dust, is a minority constituent of our own galaxy. Most of what the Milky Way is made of is something we have never directly detected and do not understand. We also do not know the precise number of spiral arms. Different surveys using different methods produce somewhat different results. We do not know the exact diameter of the disk. Estimates range from 100,000 to 200,000 light-years depending on how you define the edge. And because most of the galaxy's mass is dark matter, our estimates of total galactic mass carry significant uncertainties that no current instrument can fully resolve. What we know with confidence is this: the Milky Way is a barred spiral galaxy. At its center is a supermassive black hole called Sagittarius A star, with a mass about 4 million times that of our Sun. Around that center is a dense bulge of older stars, roughly 10,000 light-years across. Extending outward from the central bar are 4 major spiral arms, each one hundreds of light-years wide and tens of thousands of light-years long, filled with gas, dust, and the star-forming regions that produce new generations of stars. Our solar system sits in the Orion Arm, about 26,000 light-years from the center, orbiting the galactic center at roughly 230 kilometers per second. At that speed, it takes us approximately 225 million years to complete one full orbit. The last time we were in this same position in the galaxy, the dinosaurs had not yet appeared on Earth. Every image you have ever seen of the Milky Way from the outside is an artist's impression, a reconstruction built from data, an inference drawn from radio surveys and infrared observations and stellar parallax measurements and the motions of billions of individual stars. No spacecraft has ever left the galaxy to photograph it. None ever will in any time frame relevant to human civilization. The Milky Way is 100,000 light-years across. Voyager 1, the most distant human-made object, has been traveling for nearly 50 years and has covered roughly 23 light-hours. At that rate, it would take Voyager about 37,000 years just to reach the nearest star. And the nearest star is not the edge of the galaxy. It is barely past the front door. We know what our galaxy looks like, the same way a person born in a city and never able to leave it knows the layout of their city. Not by stepping back and looking at it from the outside, by walking every street, by measuring distances between landmarks, by recording where the buildings are and how tall they stand, by building a model from 1 billion individual observations, each one made from the ground, none of them offering a complete view, all of them contributing a piece to a picture that is still being assembled. That picture, incomplete and revised and constantly refined, is one of the most extraordinary things the human mind has ever constructed. A map of a place we have never seen from the outside, a portrait of our home drawn entirely from within. And with every new data release from Gaia, every new survey from FAST, every new generation of radio telescopes coming online, it gets sharper. We have never seen the Milky Way from the outside. We probably never will. And yet we know its shape. That is not a small thing. That is one of the most remarkable achievements in the history of human curiosity. If you enjoyed this video, consider subscribing. I will see you in the next one.